Welcome back, everybody. Hey, I hope everyone's not having any technical problems with Canvas. I know mine is not 100%. There's some things that not acting out properly, but anyway, we'll get through this. Okay, I think for your section, I have graded the exam. So if you have any questions about it, feel free to shoot me an email and we'll get through it. All right, so we ended up on chapter slide, I should say, 11, and we've been talking. This particular chapter deals with chemical reactions. And I stated earlier in the last time is that there are 6 types of general chemical reactions. This table here summarizes them. I'll go over it again. We did go through some of it, but it's just to refresh your memory. The first type of chemical reaction is called a combination reaction. Basically, we have 2 separate reactants, A and B, here in the generic form, that react and combine, okay, to form a new compound AB, whatever AB may be, okay? The opposite of the combination reaction is a decomposition reaction. In that scenario, a single compound is, excuse me 1 second, gotta check something. Okay, a compound in this example, general example, ABC, is heated, or a number of things can happen to it, but it breaks down to their respective components, A, B, and C, okay? Sometimes it could be A and then a BC component or A, B, C component, but you break down at least with 2, at the minimum, 2 different components of whatever the material is made up of. So decomposition reaction. The third type is a combustion reaction. As it is stated, being a combustion reaction, it requires oxygen, okay? So oxygen will always be a reactant. Now, there are a variety of different types of combustion reactions, but we're going to just deal with one type, and that is dealing with the combustion of what are called hydrocarbons. And they're called hydrocarbons because these are compounds that are made up of nothing but carbon and hydrogen. That's it. And hence you see the C and then subscript X, where X, the minimum number X is 1, and H is hydrogen, subscript Y, where the minimum value of Y is 4. So the smallest hydrocarbon there is, it would be a CH4, which is a methane, okay? But in the process of combustion of a hydrocarbon, you get, for Chem-130, only 2 products, and that is carbon dioxide, okay, and water. Those are the only 2 products that you're going to get. Yes, fully understand you use a hydrocarbon in your vehicle, and one of the gases, a variety of gases come out, but one of them is carbon monoxide. And that is because of our engine being inefficient with respect to burning or combusting the hydrocarbon that we utilize. And hence you have carbon monoxide that is emitted through your exhaust, okay? Under perfect conditions, this is what should happen, carbon dioxide. And this is one of the biggest problems that we have in combustion and in burning hydrocarbons, is the fact that you generate a lot of carbon dioxide. A lot of carbon dioxide, it's got to go someplace, and where it goes is up to the atmosphere. And it's not going to go out to space because gravity holds it on Earth, okay? And so it's going to accumulate, and eventually it's going to act like a blanket around us. And that effect results in not a lot of heat being emitted back to space like it normally does, but being reflected back onto Earth. So trapping a lot of heat, hence temperature of the Earth goes up, all kinds of problems occur. Okay, so combustion reaction. The next type is an acid-base reaction, and that is what we talked about in the last chapter, where we talked about acids and bases, okay? So we have a compound that produces an acid, normally written with H up front, okay? And that produces a proton based on the definition, the Arrhenius definition, or even the Lancet-Brauer definition of an acid is anything that produces a proton. To refresh your memory, a proton is a hydrogen atom that has lost its electron and thus has a positive charge. This is a proton. This is what causes the acidity of material. This is what's running in your stomach right now, in your acid stomach, hydrochloric acid, proton. And when that reacts with a base, and recall again the definition of a base, is for Arrhenius definition is anything that produces a hydroxide, a polyatomic ion, hydroxide ion. And when that occurs, the hydroxide reacts with the proton to give us water, okay? And so one product that's always there when you recognize if you're dealing with an acid and a base is water. And then the other product is the corresponding salt, Ma. Depending what M is the metal and A is the anion of the acid, okay? So those two get together to stabilize the charge that is produced between the positive metal and the negative anion. And again, I use the term salt because remember, salt in chemistry terms is not just sodium chloride. A salt is an ionic compound, which is made up of a metal and a non-metal. Okay? So you can have a variety of different salts. Single replacement reaction, very important here with respect to the periodic table. And I'm going to share that with you. On the periodic table, on the right below, above the solubility rules, down. Okay, we have an activity series denoted down here. Okay, and this activity series is a listing in the order of which metal is more reactive. So on the far left, this is 2 lines here, but you can stretch that out into one single line. Okay, lithium is the most reactive metal in the elemental form. All these metals are in the elemental form. Then gold. Gold is the least reactive metal. In fact, it's considered to be a noble metal because it's so unreactive. All right, and all this is relative to hydrogen, either in the form of H2 or water, H2O. And so it's a relative scale relative to hydrogen. And you can see that lithium, as I stated, is the most reactive metal. In fact, the ones in bold and then that are underlined are extremely reactive metals, in that if I put them in water, they react immediately, very aggressively. Okay, so they're very anxious to get rid of those electrons because they just react like that. The other ones, starting with magnesium and aluminum and so forth, all the way up to lead, to get those to react, you can put them in water and really nothing is going to happen. But if you put them in acidic water, it will generate hydrogen gas and cause that metal to react. They require more aggressive conditions to get them to react. And then past water, past hydrogen, you got gold, silver, mercury, and copper, silver, mercury, and gold. Those metals are extremely unreactive. And yes, we can get them to react, but they take very vigorous acidic conditions to get them to react. Okay, so using the activity series will allow us to predict whether a single replacement reaction will occur. Now, here, what we got to recognize that you have a single replacement reaction, two things. One, you have a metal in the elemental form all by itself, M. And then you have a second metal that is not in elemental form, but is in ionic form. It is a compound. It's bonded to X, whatever X may be, okay? And if you notice that here for this reaction, the way it's written, the elemental metal gets converted to ionic form and creates a new ionic compound, okay? Whereas before we start off with AX, now we have MX. And the A, which was in ionic form, now is in elemental form, okay? And a classic example of this type of reaction is plating. We're all familiar with plating, where you got maybe jewelry that's been plated with gold. Okay, that's a good example of a single replacement reaction. Okay. Then the last one we call a double replacement reaction. Okay, where both metals, now the subscript 1, subscript 2, that's not telling you the quantity of M and 1, that's really telling you two different metals, M metal number 1 and metal number 2. So to begin with, what we utilize here is the solubility table to predict as to whether a reaction proceeds. So refresh your memory on the solubility table. Remember, we've got two columns here. First column is a soluble column. Second column is the insoluble column. And then within there, we got exceptions to whether something is soluble or not, okay? So you utilize the solubility table to predict, to see if you have a reaction. And if you study this reaction in generic form, you can see that we start off with MX to begin with. In both cases, they are MX and MY, M2Y, are both soluble. We generally use, this is done in an aqueous solution, and they're both soluble in solution. They're separated. So if I had a beaker, a test tube of each one, there'd be nice clear solutions. Everything would be in solution. Okay. Now the M1 being soluble, the ions dissociate completely. They're strong electrolytes. Okay. In the process of all these electrolytes being in the solution, if I partner up with another ionic compound, in this case M2, what's going to eventually happen is the partners, the cation and the anions, are going to interchange with each other. And so now I generate MX, M1XY, and M2X. Okay. Let me make sure I got all the colors correct so we can make sure we're dealing with the right ones. Now, to determine whether a reaction proceeds, we look at the products. We don't care about the reactants because we know the reactants are soluble. It is the products. Now, the M1Y versus the M2X. If both of these are soluble, okay, if both are soluble based on the solubility rules, then we have no reaction. If one of them is soluble, and let's assume that maybe this one, M1Y, is soluble, then we put the physical state of S, means we got to precipitate. So it becomes a weak electrolyte, and it precipitates and it gets cloudy. And that would be a positive reaction, only if one of the products is insoluble in water, in an aqueous solution, I should say. All right, so those are the 6 types of general reactions in generic form, okay? So specific reactions. All right, so we're looking at phosphorus plus oxygen to give us P2O4, or diphosphorus tetroxide, okay? Now, you can see we have 2 reactants, both in elemental form, to give us a new compound, a single compound. That is a combination reaction, okay? And of course, we've got to balance it. So if you put a 2 in front of the O2, the oxygen, that balances up the oxygens. And then we put a 2 in phosphorus to balance out the phosphorus. So that is the balanced chemical reaction of an example of a combination reaction. Okay, decomposition reaction. We have this compound here, F2O3. One second. And that would be iron, Roman numeral 3, oxide. Okay, you might want to go refresh your memory as to how I got that figured out real quick as far as the name. So iron 3 oxide, otherwise known as rust. Okay, good old fashioned rust. Had an old pickup, had a lot of iron 2, not a pickup, old truck that had a lot of iron 3 oxide on it. If we take the compound, the reactant, and in this case we can heat it up, we actually break it apart. We break it back into the elements. We create iron and oxygen. Okay. It's another thing we could do. If you probably find a lot of iron 3 oxide out there in other planets. We can utilize it to generate oxygen, so we can use it to breathe. All right. And of course, we got to balance it out. And so we have 2 iron 3 oxides to give us 4 irons and 3 oxygens. Okay. Now, how was that done? Well, look at here. If we look at the oxygens, okay, we can see we got 3 on the reactant side, 2 on the product side. If we find a common number, we can put a 3 in front of the oxygen right here, and the 2 right here. That gives us 6 oxygens on the left side, 6 on the right side. That kicks up our iron to 4, so we simply put a 4 right there, and we're balanced. Okay, combustion reaction. We have this particular compound, C3H3. Okay, sitting right here. This, by the way, if you're going to do some barbecuing this weekend and using gas, that is the formula for propane, good old-fashioned propane. But recognize the fact that you have nothing but carbon and hydrogen. Therefore, it is a hydrocarbon. Okay, there are a variety of different types of hydrocarbon. That is the generic name for these type of compounds. They're under organic chemistry domain. Okay, combustion. The term combustion to tell you, okay, I need oxygen. Okay, I need oxygen because I'm going to burn this thing. And what I stated earlier about burning of hydrocarbons, guess what? There's only 2 products. Yeah, carbon dioxide plus water. Okay, and so that is the beginnings of writing what you just see here in yellow into an equation. We got that hydrocarbon, it's a combustion, I need oxygen. Those are the only 2 products I'm going to create. And so now I can simply put the hydrocarbon in there, and that is my generic equation. But I got to balance it. Now, when it comes to balancing hydrocarbons, we have a very systematic approach to it. Okay. All right. The systematic approach is this. You first balance the carbon. Okay. So you notice here, I got 3 on the left, I got 1 on the right reactant. So I balance the carbon first. So I got to put a 3 there. Okay. Then I balance the hydrogens. Well, okay, I got 8 on the left-hand side in the form of C3H8, and I got 2 in the form of water. Well, to balance the hydrogens, I just simply put a 4 in front of water. That gives me 8 hydrogens okay? And I got 3 carbons. And then finally, the last thing you balance are the oxygens. So we got to count out what we have. We got two oxygens in the reactant side. On the product side, we got 6 coming from carbon dioxide and 4 coming in the form of water. So we have a total of 10 oxygens. Okay. So to balance 10 oxygens, I simply put a 5 right there. And that gives me 5 oxygens inside. Okay. So, or hydrocarbons. Once you write down the reaction, which would be the hydrocarbon plus oxygen, whatever that hydrocarbon is, then the products you always get for Chem 130 is carbon dioxide and water. Once you got the reaction worked out, then you balance it and you use the approach of first you balance the carbons first, okay? Then you balance the hydrogens. Then at the end, you balance the oxygens and you're all set to go. Now that will work for you. All right, let me clear this up a little bit. All right, so there's the reaction we just did. Obviously, I forgot the physical states because we're burning this, so obviously everything is going to be in the vapor phase. Okay, and then we balance it. We balance it simply by going through the steps of carbon first, followed by hydrogen, followed by oxygen. Okay, and that's what this slide's telling you. For the combustion of hydrocarbons, carbon, hydrogen only. All right, let's do one more. All right, the acid-base neutralization reaction. And as we talked about that, you have to recognize that you're dealing with an acid, which is H there, and the hydroxide, which always gives you water. Okay. And so we look at the typical reaction. Now, how to balance these types of the reactions? How? Follow the protons and the hydroxides. Balance an acid-base reaction. You do that, it's just going to naturally fall in place. Okay, as far as the other ions coming into play. All right, let's take this example here. Well, we have HCl, hydrochloric acid. Okay, and we know got hydrogen written first. That's a proton. It's also we talked about HCl in the past. It's a strong acid. Second one. You may not recognize it at first, but the fact is, if you name it, it would bring shooter memory for you. But if I were to name this, I need to know what's in the parentheses. And again, that's a hydroxide. So we got barium hydroxide. So we have the hydroxide and we have the proton. We know that the hydroxide and the proton will always create water. So you can put that down as a product. And it's going to create the salt. Now, my suggestion first, before you write the formula, is you put the salts in ionic form. And so we know that barium is in group 2, so it's going to be a +2 charge, right? But if you didn't know that, look at this. The hydroxides are each a -1. You can find that on the polyatomic ion table. It's a -1, and there's 2 of them. That means that infers that barium must be a +2. Okay, so it's a +2. The proton, always, we know that the proton's a +1, but not only that, the chlorides are always a -1. It's in group 7, right? The chlorine is in group 7, it becomes chloride, it gains 1 electron because it's a nonmetal. That's a -1 charge. So those are going to be the corresponding salts that may appear in the general formula, but I write them first in ionic form because I want to make sure that I put them together properly with the correct number of cations and anions. So that tells me that I'm going to need 2 chlorides and 1 barium. So I can write the formula as BaCl2. Okay. So I got the general formula written down. Now, as I stated, follow the protons and the hydroxides so you can balance this out. Well, we start off with 2 hydroxides. Okay. I need to neutralize those 2 hydroxides. What does that tell me? That means that I need 2 protons. So I can put a 2 in hydrochloric acid. Okay, that's going to give me 2 protons to neutralize the 2 hydroxides. So if I have 2 protons and 2 hydroxides, guess what? I'm going to make 2 waters. All right. And so now I just look around and I say, oh, maybe I'm balanced already. Well, let's go. Let's check it out. I have a total of 4 hydrogens in the form of water. Okay. And as reactants, I got 2 hydrogens in the form of hydrochloric acid and 2 hydrogens in the form of the hydroxide. So guess what? My hydrogens are balanced. My oxygens, I got 2 oxygens in the form of water. And reactant sides, I got 2 oxygens in the form of the hydroxide. So they're balanced. So you can see by following the proton and the hydroxide that automatically I got my hydrogens and oxygens balanced. We'll go back and check the barium. We got 1 barium as a product, 1 barium as a reactant. We're good with that. Then we got a 2 in front of the hydrochloric acid, which tells us we got 2 chlorides. Well, guess what? We got 2 chlorides in the form of barium chloride. We're balanced. Okay. We're totally balanced. And I'll do the slide here in a second. Let me continue with the next one. All right. So now the second part. Let me make this a different color so we don't get too mixed up. All right. So as I stated, follow the protons and the neutrons. We have H3PO4. Okay. Now you may not remember what that is. That's okay, because you can see you got a hydrogen written first, like we did with HCl, and then followed by whatever is there, PO4. This is phosphoric acid, by the way. We talked about that, but there's 3 hydrogens. Then we got calcium hydroxide. Okay, the other base. All right, that's also found in Tums, by the way. Okay, so now I got a dissimilar number, but like we've been doing before, when we got 2 dissimilar numbers, like 2 and 3, what do? We look for a common number, right? So I can put a 3 in front of calcium hydroxide. That gives me a total of 6 hydroxides, does it not? And I can put a 2 in front of phosphoric acid, because now that gives me a total of 6 protons. So now I got 6 protons, 6 hydroxides. I know that I'm going to make water. And guess what? I'm going to make 6 of them, 6 molecules of water. All right. Now, the calcium, before I put them together, what I want to do is first write them in ionic form. I know that calcium is a +2, like in barium, it's a +2, it's in group 2. And the PO4, guess what? That is the phosphate ion with a -3 charge. Remember that guy in the polyatomic ion? All right. Table, the phosphate has a -3. If I put those 3 protons back on to phosphate, I got phosphoric acid. Right. So I got a dissimilar thing here. So I got, I need a common number for the ions, and the common number here again is 6. So that means I need 2 phosphates and 3 calciums. So therefore, my formula would be calcium 3PO4. Because I need 2 of them, I use the parentheses, okay? And so that is my formula. Now we check to make sure that everybody's balanced, all right? So the fact that it had 6 protons, 6 hydroxides tells me I'm going to make 6 water. So guess what? My hydrogens and my oxygens are balanced. You can go back and check those individually if you like. Calcium, I got 3 in the reactant side, 3 in the product side, and the PO4. You can count each one. You can count each one individually, each phosphorus, each oxygen. But when you're balancing polyatomic ions, just balance the whole unit. So I have 2 PO4s in the form of phosphoric acid, and guess what? I have 2 PO4s in the form of calcium phosphate. So now I got a balanced chemical equation. Okay. So let me clear this mess up and bring in the slide. Okay. There you go. Now I did forget the solid for calcium phosphate. My mistake. But how do I know it's solid and not AQ? Now I will go to the solubility table, and I will see that calcium phosphate is insoluble, therefore it's a solid. Okay. Notice the H2O here. It's an aqueous solution. It's a liquid. You're making water, which is a liquid. We're not a gas. We're not working high temperature here. We're working in an aqueous solution. Sorry, room temperature. Okay. So for acid-base reactions, to balance them out, 2 things: follow the protons and the electrons. Okay. And then the particular salt that you create, first write them in ionic form, so to make sure that you put them together properly in the correct ratio. All right, single replacement reaction. We also have a stepwise procedure for this particular reaction. Okay. Now, here's a generic formula. We got M plus AX to give us MX plus A. If this reaction proceeded, notice that the metals, which are denoted both by the letter M and the letter A, they interchange position. The M starts off as the element and now becomes ionic. Okay. And A, which starts off as ionic, now becomes the element. Okay. So you exchange partners, and like I stated earlier, this is like a plating. This is a plating reaction, actually, where A is what you want to have plated, be it gold, be it copper, be it chrome, be it whatever you want to plate. Okay, and the other aspect is we use the the activity series to determine whether this reaction occurs. Okay. For this reaction to occur, what we do is we look at the metals and determine which is the most reactive metal. So in this generic formula, we will say, okay, which metal is more reactive, M or A? Now, we know A is in the salt form, but we don't care about whether it is salt form or not. We just want to know which metal is more reactive. And once you determine which metal is more reactive, then you ask the second question. Is the most reactive metal in ionic form? Is it a compound? And if the answer is yes, then there's no reactant. If the answer is no, then there is a reactant. Because the driving force, the most reactive metal, which in this scenario would be M, wants to become ionic because it's more stable in ionic form. So therefore, if it interacts with the salt that contains a metal that's less reactive than M, it would exchange partners and the reaction proceeds as written. Okay. All right. So we talked about this. Here's the activity series. We got lithium is down the most reactive, and we got gold all the way to the far right. Okay. All right. So steps. Check the activity series to see which metal or hydrogen, it could be a hydrogen or water, okay, is more reactive. We have some examples to show you that. And then the most reactive, but the most active metal wants to be in the compound form. If it's already in the compound form, then there's no reaction, as I stated. If, and then we write the letter NR, meaning no reaction, okay? The partners are not switched. But if it's not in ionic form, then reaction proceeds, okay? And then we write the correct product formulas, and we make sure the new compound we make, the new ionic compound we make, put those first in ionic and ions so we can put them together in the proper ratio. Okay. Then of course we add the states for whatever they are. And then of course we balance it. All right. So let's take this reaction here. This reaction, we have zinc nitrate in the presence of sodium. Okay. Zinc nitrate in the presence of sodium. And so what we are interested in is just the metal. In this case, we're going to compare zinc versus sodium on the activity series. So we got to find it. Here's zinc right there. And here is sodium. And so obviously sodium is more reactive, much more reactive than zinc. Okay. So we write that down. Let me do this. And so step number one, we determine that sodium is a lot more reactive than zinc. Okay. Question. Second question you ask yourself, sodium, is it in ionic form? Is it a compound? Okay, that's the question you ask, because sodium is the most reactive. And in this case, question number 3, sodium, no, it's not in ionic form. It is in elemental form. So no to number 2, therefore reaction proceeds. Reaction, yes, we get a reaction. All right. And so we're going to, let me rewrite this. We got zinc nitrate plus sodium. And we're going to change partners here. And so zinc, which is in ionic form, now becomes zinc in elemental form. And then sodium goes into ionic form. So we first write the ions first. We know sodium has a +1, okay? And the nitrates, we know that those are NO3 minus, okay? To refresh your memory, go to the polyatomic ion table and you'll see NO3 has a -1, okay? So we're gonna put these together, they're simply a 1-to-1. And so the formula here would be NaNO3. Okay. Now we got to balance it. So our zinc is okay. Got one zinc here, one zinc there. Nitrates, remember, the polyatomic ions don't separate them. Treat them as one unit, and even when you're balancing them. So you can see we had 2 nitrates. So if I simply put a 2 here in front of sodium nitrate, that balances my nitrates. Well, in doing that, that kicks up my sodium count. Okay, no big deal. Then we come over here and put a 2 in front of sodium. Okay. And guess what? it now is balanced. I got one zinc, two sodium, two sodium, two nitrates, two nitrates. Okay. Now it's a matter of putting in the physical states. We know that aqueous, zinc nitrate is aqueous, it's given to us, and sodium is solid, it's also given to us. All the elements, all these, sodium is a metal, we know that, okay? Aqueous. Now the question is, what about in the products? Well, zinc, being one of these, being a metal, there's only one metal that is a liquid. All the other metals are solids. That's a solid, right? And then we look up sodium nitrate. Well, how do we know what to assign it? Well, we go to the solubility rule. And remember in the solubility rule, in the first column, number 1, sodium was one of the big four, top 4, right? Anything bonded to sodium is soluble. So we will have AQ here. I'll bring up the other, my hand. My resolution in my pad is not the best. You might be seeing kind of jagged images. Let me clear it up and I'll bring in the slide. So that is what we just did. Okay. We put the physical states. Zinc is solid and sodium nitrate based on the solubility rule is soluble. Therefore we use AQ. And then I went through the scenario of balancing the equation. In this case, we followed the polyatomic ions. So we can balance it out, and it just by default everything just fell in place. Okay. Obviously, this would be incorrect. Na parentheses NO2, because we know that sodium is in group 1. It only has one valence electron. Okay, so it's going to be a +1. The nitrates are each a -1. Okay. Check the polyatomic table. You see nitrates are a -1 polyatomic ion. There's 2 here in the parentheses. That infers that sodium must be a +2, which it can't be because it's a group 1 element and there's only one valence electron. So this should be totally incorrect for a formula for sodium nitrate. All right, so they all fall in place. Let's take a look at this one. Got strontium bromide and aluminum. Okay, so let's find them. Okay, so we find aluminum sitting right here. Okay, and strontium sitting right there. So, number 1, SR is a lot more reactive than aluminum. Okay, based on the activity series. Step number 2, strontium is in ionic form. It is an anionic compound. It is in the form of strontium bromide. Therefore, the most reactive metal is already a compound. It's no longer an elemental form. Therefore, guess what? We get no reaction. Okay? No reaction. Now, let me get this here. No reaction. Because strontium SR is a lot more reactive than aluminum. And SR is already in ionic form. It's in the compound form already. So it's in this most stable form. So you get no reaction. But what does this mean for the opposite reaction? Okay, because if it's written in this manner, then the opposite reaction would work, right? The opposite meaning this: if I had aluminum bromide plus strontium in elemental form is solid, okay, and this would be aqueous. Yes, you would get the reaction. In fact, the reaction products you would get will be these guys: aluminum metal and strontium bromide. Why? Because strontium is the most reactive metal in this reaction, the second one I wrote in blue. And 2, it is not in, it's in elemental form, not in compound form. So reaction proceeds. Okay. So when the forward reaction in one has a no reaction, then the opposite reaction, yes, it would react. Okay. All right. How about this one? Now, a little bit more challenging, okay? Just a little bit. But that's okay. So what you're doing here, in the past, we were, remember our activity series relative to hydrogen. Okay. And hydrogen could be in the form of water, or it could be in the form of H2. Okay. So in this example, what we're doing is we are comparing hydrogen versus aluminum. Hydrogen versus aluminum. You can see the activity series that aluminum is a lot more reactive than hydrogen. Let me emphasize that. Here is aluminum, okay, and here's the hydrogen. Aluminum is a lot more reactive than hydrogen. So the question then asks, is aluminum in ionic form? And the answer is no. Okay, it's not in ionic form. And so that means that this reaction will proceed. And the hydrogen, which is the proton form, which is converted back to the elemental form, will be hydrogen gas. Okay, that's where sometimes the troubling part is. Well, wait a minute, we have an acid, and so when the metal that you're reacting with the proton is a lot more reactive, then the reaction will proceed. And the product that you will get when you're in the form of an acid, the H becomes H2. Okay. Plus, now you exchange with the aluminum with the hydrogen. And so we need to put together aluminum chloride. But like before, we first put them in ionic forms. Aluminum is a +3. We know that the chlorides are each a -1. Okay, so we need 3 chlorides for the +3. So our formula will be aluminum Cl3. Okay, now we got to balance it. Okay, I got 3 chlorides here, 1 aluminum. The aluminums are okay, but then I got 2 hydrogens and 1 on the left side. I got to play with the numbers a little bit. You know, how do I do this? Well, I can take the chloride and increase the chloride, right? Could I do that? Yeah, why not? But then if I do that, if I put a 3 in front of HCl, that gives me 3 hydrogens, but I only got 2 hydrogens. A little bit of a challenge here playing with the numbers. So what would you suggest? Any ideas? How can I balance this? You know what I'm saying? I got 1 aluminum on each side, so they're good. The chlorides and the hydrogens can be a little bit challenging. Anybody have any suggestions? What will work? Oh yeah, the physical states. Would that work? Okay, see how they did that, but let's work this through first. And tell you what, why don't you think about this one here? All right, and then on Tuesday we'll come back and go over it, because this is probably going to be the most challenging one to balance. The other ones were pretty straightforward. You know, we had the combustion where I gave you a stepwise. The acid-base reactions, I tell you to follow the proton and the hydroxides. These double replacement reactions, we follow the polyatomic ions to get them balanced. The other ones, there were small enough numbers that we can just use a simple trial and error. It looks like we may have to do the same thing here. Okay, trial and error. So think about this one. See if you can get a balance on your own, and see if you come up with the same number. So it's going to take 2 aluminum, 6 hydrochloric acids, 2 aluminum chlorides, and 3 hydrogen gas. Get that thing balanced. Okay. One word about balancing is sometimes, like in mathematics, you know, when you're trying to you reduce numbers to the lowest terms. In other words, you can come up with, let's say, a 4 here, 12 here, 4 here, and 6 here, which it is balanced. But convention, take your coefficients, if they can be reduced to the lowest terms, then do present your balanced chemical equation in the lowest values, in the lowest terms. And so, yes, sometimes occasionally you come up with 4, 12, 4, and 6. Look and see if anything's divisible further down, and bring it down to its lowest term, which would be 2, 6, 2, and 3. That's as low as you can go. Whole numbers, no fractional numbers, no half numbers. Okay. Yeah, there's YouTube's Dr. Kim Smith on her presentation of reaction. Do look at them. More information for you, different way of presenting these reactions. Okay. With respect to a single replacement, it's a flow chart. You can, once you determine which metal is the most reactive, then you ask the questions. If it's the most reactive metals in salt form, then you get no reaction. If it's not in salt form, then you do get a reaction. And what you do is that metal that was ionic to begin with now is elemental. And now you make the other metal now becomes ionic. So write them first as ionic form so you can put them together with the correct ratio of cations and anions. Okay. All right. The double replacement reaction. This reaction is dependent on the solubility rules. So when you see a double replacement reaction, what you rely on is the solubility rules. A single replacement, remember, recognize that you have one metal that is an elemental form sitting there all by itself. That should flag for you that I'm dealing with a single replacement reaction. With double displacement reactions, you'll find the 2 reactants are very soluble in water to begin with. Okay, and then most of the time they're going to be polyatomic ions attached to the compound. Not always, but you tend to pick up a trend of these types of reactions. But the point is, solubility rules are what play a factor to determine whether a double replacement reaction will proceed. Okay. Notice this reaction here, AX, very general reaction. BY, those are 2 reactants that are coming together. They're both aqueous, implying that they're both soluble in water. Okay. And in fact, if you had them together, they wouldn't be put together in the same container, it would be in separate containers. both soluble solutions. Okay, you put them together, mix the two beakers or whatever you're testing, put them together, and what happens if it's a positive reaction? You get a precipitate, and it's cloudy. Okay, and you in effect have caused the cations and anions to change partners. So AX now becomes AY. BY now becomes BX. Now, in the solubility rules, BY happens to be insoluble. Hence, you got an S. Okay. And in the solubility rules, BX happens to be soluble. And since we're dealing with an aqueous solution, you got an AQ because it is soluble. Now, and this would indicate a positive reaction. The thing to remember about double replacement reactions is if the products, again, we're only dealing with the products as far as solubility. If one of the products is insoluble, it's a positive reaction. If both of the products are soluble, if they both dissolve and are shown to be from the table that they're soluble, you get no reaction. All you do is just change partners, nothing happens. You're looking for an insoluble product. Okay. All right. We call these precipitation reactions because there's a solid that is formed. Okay. This is basically all that I just explained. You get a solid because solubility, it's a reaction. Both of them are soluble, no reaction. All right. So learn the solubility rules, and let's go back and quickly refresh our memory on that. Okay. And I'll go through it quickly. I know we've done it before, but just to refresh your memory. We have two columns here. First column, the highlighted in blue, is the solubility column. Now, any of the cations, the positive charged cations, are bonded to whomever. It doesn't make any difference what they are. If it's lithium, sodium, potassium, and ammonium as the cation, always 100% soluble. Okay. Any of the cations, regardless of what they are, that is bonded with the acetate ion and the nitrate ion, 100% soluble. Okay. Same is true for the chlorides, the halides, I should say. Normally, the chloride, the bromide, and iodide, when they're bonded to everything in the world, so to speak, to say, they're soluble except if they are bonded to silver, mercury, and lead. Okay, those three examples, any of the halides, the chloride, the bromide, the iodine, if they're bonded to lead, mercury, or silver, insoluble. Everything else is soluble. The sulfate, also similar to the halides, are soluble unless they are bonded to calcium, strontium, barium, silver, and lead. Then they are classified as insoluble. Okay, so copper sulfate, soluble. Lead sulfate, insoluble. Now, on the other side of the table is the insoluble table. Right? Now, the carbonate. If you have a carbonate in there, always insoluble except, and I repeat that, except if they're bonded with the big four. So lithium, potassium, sodium, or ammonium carbonate are soluble all the time. Those are only 4 examples. Everything else, insoluble. Copper carbonate, insoluble. Magnesium carbonate, insoluble, etc., etc. Same is true with chromate. Chromate, all examples out there are insoluble except if they're bonded to the big four. All right. Same is true with phosphates. Phosphates are always insoluble except if they're bonded to the big four. And the sulfides, that's the S-2, are also insoluble except if they're bonded to the big four and bonded to calcium, strontium, and barium. So there's only 7 examples of sulfides that are soluble. Everything else is insoluble. And the same is true for the hydroxide. Insoluble unless they're bonded to the big four or calcium, barium, and strontium. So again, there's only 7 examples of hydroxide compounds that are soluble. All the 10 billion, whatever other hydroxide compounds out there in the world are insoluble. Okay. So that's a quick refresher on the solubility table and how to use it. Oh, let's take these here. All right, we got barium nitrate plus magnesium sulfate. Now, bear in mind what's going to happen is that the barium is going to exchange with the recombine with the sulfate, and let me change the color here. The magnesium would then combine with the nitrate. Okay, so those are our new products that we would make. All right, so let's write those down. And so we have now barium. Now, before we can do it, I strongly recommend that you first write down the ions, okay? And we know of all of them, okay? Because we know that the sulfates are -2 and the barium is a +2. And magnesium is a +2, right? And the nitrates are all -1. So those are the ions. I want to write them in ionic form first because I want to make sure that I put them together properly. And so if we look at barium and sulfate, we got a barium with a +2 and the sulfate with a -2. So its new product would be this. Okay. So I'm writing the formulas first of what the potential products, new products would be. Okay. So the next combination is the magnesium and the nitrate. Well, I know that the magnesium is a +2 and the nitrates are -1, -1 each. I need 2 of them. So I need, my formula would be magnesium nitrate, parentheses, the 2. Now the question is, let's look at solubility. Is this reaction going to proceed? Because if it doesn't proceed, there's no need to go any further to balance it. So we look up magnesium nitrate. Remember all the nitrates? Number 3, all the nitrates are soluble, regardless of what they're bonded with, okay? That means that magnesium nitrate here is soluble. We can put AQ. Now we look for the sulfates. Normally, all the sulfates are soluble, okay? Unless they are bonded to calcium, strontium, barium. There it is right there. Barium sulfate. That means that barium sulfate would be insoluble. We put an S there, okay? So now we know that this reaction will proceed. This would be a positive reaction because barium sulfate, one of the new products, is insoluble. Now we need to balance things out. And by default, guess what? Things balanced out. Follow the polyatomic ions. We got 2 nitrates to begin with here as a reactant. Guess what? We got 2 as products, okay? We got 1 sulfate. We got 1 sulfate, okay? 1 mag, 1 mag, 1 barium, 1 barium. Guess what? By default, just putting them in the proper formula. In this example, it balanced by itself. Let me clear it, okay? And that's our equation. It's a positive equation, okay? And the reaction in this case just happened to balance itself out. So that's why it's important that when we write the new products, we put them in ionic form first so we can put them together properly. Okay. All right. Let's take a look at this one. We have lead nitrate, aqueous, and potassium iodide. The fact that you see lead to begin with, pretty a good indication that we might get a precipitate here. But before we do all that, until you get comfortable in putting these all together, let us first write the ions. So let's take a look at lead. How do we know what is the oxidation number on lead? Well, guess what? Nitrates each have a -1, right? There's 2 of them. That infers that lead is a +2, okay? The nitrates, as I stated, I'm going to put over here, each have a -1. Now we're going to exchange partners. So the lead now is going to partner up with the iodide, and the potassium is going to partner up with the nitrate. So the iodide is a -1 because it is a group 1 element, right? Group 7, excuse me. It's a nonmetal, it gained 1 electron. So it's got a -1 charge. Okay. And then potassium, that is a group 1. That's where I was thinking in my head here. That's why it came out wrong for the iodide, is a +1. Okay. And so now I got them all written down as ions. So now if I put lead and iodide together, I need 2 of those. Potassium nitrate, it's a simple 1-to-1. So to write the formula, I got PbI2, okay, and then plus potassium nitrate. So I've written the formulas. Let's go check the solubility now before we proceed. Look at potassium nitrate. Potassium has a straightforward potassium. It is part of the big 4. It's automatically soluble, aqueous. Okay. Iodide. We look for the halide ions. Here's iodide. Normally they are soluble unless they're hooked up with bonded with the heavy metals, specifically lead. Guess what? Lead iodide is insoluble. So we got a solid. So in this example, we have a reaction, positive reaction. Now let's balance it. Follow the polyatomic ions. We had 2 nitrates right here. Okay. That means I can put 2 in front of potassium nitrate. Okay. That balances the nitrates. Well, that kicks up my potassium. So now I got to increase my potassium by putting the 2 in front of potassium iodide. When you do that, that kicks up my iodide, but that's okay because by default, I got PbI2. So my iodides are balanced, my lead's balanced, my potassium's balanced, and my nitrates are balanced. So everybody's balanced. And now let me clear my table here and bring in this slide. And we got it right there. Okay. Positive reaction. All right. All right, let's do one more. And then we got a few others that we're going to work with. We got barium chloride and silver nitrate, both soluble. All right, so systematic approach. I always advocate that so we know what's going on here. So we're gonna take the barium and we're gonna change partners with the nitrate, and then the silver is gonna interact with the chlorides. Okay, but let's write the ions first to make sure that we got them put together correctly. And so we got barium, which is a +2, okay? And we know right now, hopefully nitrates is a -1. And then silver is one of the elements that always has a +1, right, for the metal. And the chlorides always have a -1. Okay, those are the new partners. So Let's write them down. The barium nitrate. Well, I need 2 nitrates for the barium. So it's BaNO3 subscript Q. And then the silver chloride's a simple 1-to-1. Okay. Those are my 2 new products. Let's check solubility. All right. So barium nitrates, regardless of who the nitrates are bonded to, always soluble. So we got AQ here, that's soluble. Okay. The halides, the chlorides, okay, normally soluble, except when they're bonded to silver. Guess what? We got silver chloride, solid. There it is. Okay, now we got a positive reaction. Now we got to balance it. Okay, we got 2 chlorides here. Oh, 2 chlorides here. 1 barium, one barium, 1 silver. Those are balanced. I got 2 chlorides here. Well, what if I put a 2 in front of silver chloride? That balances out my chlorides, which picks up my silver. So if I put a 2 in front of silver nitrate, that balances out my silver. And guess what? That gives me 2 nitrates at the same time, which balance out my barium nitrate. All right, let me clear up my mess and we'll show you a little bit cleaner formula. There you go. All right, so we got a positive reaction. It's about that time. All righty, well, I tell you what, let's stop it here. This will be slide 28. We'll continue this on Tuesday, excuse me. And I got to go out and get me my shot here at 2:45. Hopefully I won't turn into a zombie. I'll be here Tuesday, okay?